Okay, great. So welcome back, everybody, after the summer break. I'm really happy to welcome Tevian Dray to give the 13th OSMU lecture on a division algebra description of the magic square, including E8. Tevian is currently professor of mathematics at Oregon State University, and his research interests are in classical general relativity, geometry, and mathematical physics, including octonions and their applications to the standard model. I first met Tevian way back in 1987 when I was a graduate student at the Tata Institute, and Tevian and Corinne came and spent a few months at the Institute visiting my supervisor, Thanu Padmanabhan. Since then, our paths have crossed very many times at one conference or the other, especially because Tevian loves coming to India and has been here several times. I first became aware of his work on the octonions only 3 years back, and I'll forever be in gratitude for the important paper he and Corinne wrote on the eigenvalue problem for the exceptional Jordan algebra. Tevian obtained his BS from MIT in 1976 and his PhD from UC Berkeley in 1981. His dissertation was on the asymptotic structure of a family of solutions of the Einstein-Maxwell equations. Since then, Tevian has worked at very many universities across the world, including Clermont-Ferrand in France, Trier in Berlin, and also Utrecht, Lancaster, and Adelaide. He has also worked with very many different researchers, including Gerhard Tooft, Abhay Ashtekar, George Ellis, Paul Davies, Carlo Rovelli, and Corinne Minogue. Amongst his well-known works are the gravitational shock wave of a massless particle jointly done with Gerhard Tooft, angular momentum at null infinity with Strubel, and the rotating quantum vacuum with Paul Davies. Tevian has authored several books, including Geometry of Special Relativity, Differential Forms in the Geometry of General Relativity, and the very important book on the geometry of octonions, jointly written with Corinne. Tevian has also contributed extensively to the cause of education in the fields of science and mathematics. He's a recipient of the Heimer Distinguished Teaching Award from the Mathematical Association of America and is also a fellow of the American Physical Society. On a personal note, I want to add that Tevian is one of the kindest and friendliest researchers I know, and behind the gentle exterior, there lives a researcher of very formidable talents. Over to you, Tevian. Good to have you with us.
Thank you, Tejinder. And again, my apologies for the technical issues this morning. I always laugh to myself when I see other people having difficulties and saying, no, it's not going to happen to me. So I will gather my thoughts. I apologize if I'm a little bit discombobulated. I'm using unfamiliar software on an unfamiliar computer, but we'll see how this goes. So what I'd like to share with you today is some work that has been done with Rob Wilson and Corinne Minogue, just in describing the exceptional Lie group E8 using the octonions. And let me just start with a few acknowledgments. Okay, there we go. First and foremost, to Rob himself, this description of E8 is his original idea. And Corinne and I had been working for years on E6 and did not see how to move forward. And it was Rob who provided the key insight that allowed us to do so. David Fairley and Tony Sudbury are the ones who got us interested in octonions back in the 80s. Paul Davies, David Griffiths, Jim Wheeler explained various pieces that all show up here. A number of students, I won't read the whole list that we've had over the years. Other collaborators, John Huerta and Susumu Okubo, and last but not least, FQXI and the John Templeton Foundation, as well as the Institute for Advanced Study for financial support. Okay, with that out of the way, let me jump in and give you a bit of a recap. The first couple of slides should feel fairly familiar to those of you who have done research on the Octonians or who have looked at them before, but let me set the stage anyway, both to set notation and because there are a couple of twists along the way. Let me, as an aside to Ginger and Michael, I'm not monitoring the chat, but do feel free to let people interrupt with questions at any point.
Okay.
So the real numbers, quaternions, complex numbers, octonians, these are old friends to most of us, but many of us don't pay as much attention to their split cousins. And so I will spend just a couple of minutes telling you some of their properties. When you go through the Cayley-Dickson process to generate new division algebras from old, you have a choice as to whether you add more units that square to -1 or units that square to +1. And you get the split algebras if you stick in a unit that squares to +1. We will call it capital L in analogy with our favorite name for the last ordinary octonionic unit, script L. But I want to emphasize that it squares to +1 in the context of the split octonians. We'll write the unit as capital U so that we can distinguish the unit in O prime U from the ordinary unit in O, which we'll write as 1. The split division algebras have signature 4, and you'll see in a moment that this allows us to consider non-compact forms of the exceptional Lie groups, but they're not, strictly speaking, division algebras. In particular, they have null elements, elements that square to 0, and they contain projections. And those two features are crucial aspects of the transition from the ordinary division algebras to the split algebras. All right, before I go any further, let me tell you what I'm going to do and what I'm not going to do today. The goal is to describe a particular real form of E8 in terms of 2 copies of the octonians, 1 split and 1 not split, and then to show how that exceptional Lie group, we'll mostly be talking about the algebras today, how that exceptional Lie algebra splits up naturally into a piece that describes the groups of a grand unified theory and the spinors that go with that theory. And that grand unified theory is ultimately a theory involving SO12-4, which contains both the standard model groups and the complex numbers in a way that I will come back to. But let me emphasize, coming down here to the end, that I'm not going to talk about the physics today. Okay? You may have noticed that Corinne is also giving a talk in the series in October, and we've split our content, as we did with the papers we published last year, into 2 pieces. I'm going to be talking about the mathematics that underlie the structure of E8 today, and Corinne will then start there in about a month and talk about the physics consequences. So you'll see glimpses of it today, but only in the sense that we will see the standard model groups showing up. And then finally, I know that there's considerable interest in looking at Jordan matrices, studying the Albert algebra, the minimal representation of E6. Ginger in particular has been using those ideas in order to try to explain particle masses. And so I want to spend some time near the end today showing how not only E6, of course, sits inside E8, but the Albert algebras, the minimal representation of E6, sits inside E8. That one of our punchlines is that E8 is everything. E8 has the groups you want, E8 has the symmetries you want, but it also has the representations of those symmetries. The Albert algebra in the case of the Jordan matrices that Tejinder's working on, the spinors in the case of the standard model. It also has the representations in it that you want to use to do physics with. Okay. So our starting point is the well-known Freudenthal-Tietz magic square. This is work that was done in the 60s independently by Freudenthal and Tietz. And the basic idea is that you can parameterize a certain set of Lie algebras in terms of two-division algebras. And you all presumably know, it is well known, there are precisely 4 division algebras over the reals, the complexes, the quaternions, and the octonions. So you get this nice table of, in principle, 16 elements. What is remarkable about the magic square is that it contains 4 of the 5 exceptional Lie algebras, F4, E6, E7, and E8. G2, the one that's missing, of course, is also octonionic. It's the, as a group, the automorphism group, as a Lie algebra, the derivations of the octonions. And so this was possibly the first place where the connection between the octonions and the exceptional Lie algebras was really made clear. These Lie algebras are normally presented as complex algebras. You construct the infinitesimal group and then you complexify. We will be interested in real versions. There are actually 3 versions of the magic square, depending on what combination of division algebras and split division algebras that you use. But our guiding principle number 1 is that we're going to only work with real Lie algebras. Okay. And the reason for this is pretty obvious. We'd like to get special relativity in the game. We'd like to get the Lorentz group in the game. And in order to do that, we need to be able to talk about the difference between boosts and rotations. And so we need to be able to talk about signature. The complexification eats the signature. You don't see the signature anymore after you've complexified. So we're going to look at the half-split real form of the magic square. And I've listed the standard names of the groups of the Lie algebras, that show up in sort of the 3x3 block on the left, and then the real forms in this killing carton notation. F4 is still the compact form in the top right, but it's so-called F4-4 in the bottom left. The number in parentheses gives the difference between the number of boosts and the number of rotations. I'm using boost and rotation as generic names for symmetries that square to +1 or -1. If you like, you can think of those as Hermitian and anti-Hermitian matrices, except I'm going to pull that rug out from under you in a moment. Okay? And I've listed some of the folks who worked on this at the bottom, notably Barton and Sudbury in 2003, who really gave the sort of complete discussion of the magic squares from this point of view. And the number of our colleagues, including my PhD student, Aaron Wongberg, who worked on E6, and at the bottom, the paper with Rob Wilson, where this work is laid out in detail. That paper's in JMath Phys and is on the archive. I've got the reference, I think, on the last slide. So let me back up and talk about what we like to call, and I think Barton and Sudbury called, the 2x2 magic square, where you look at what amounts to a sub-piece, a smaller version, sub-algebras of the algebras in the Freudenthal-Tietz magic square. It has a similar parameterization corresponding to these Lie algebras here. If you know the Killing-Carton classification, you'll recognize that most of these are orthogonal groups of various kinds, and they all admit a description in terms of Clifford algebras and division algebras and spinors, which was explored notably in some work with John Huerta and my graduate student Joshua Kincaid almost a decade ago. And in that Clifford algebra description, you wind up thinking of this magic square as the following collection of orthogonal groups, orthogonal Lie algebras. One of the first things to notice here is that if you look in the second row, you see the 4 Lorentz Lie algebras corresponding to 3, 4, 6, and 10 dimensions, parameterized by the 4 division algebras. This work was used by Corinne and collaborators in the 80s and 90s to talk about string theory, and it was realized by those folks and others that an octonionic parametrization explains why classical supersymmetry only works in those 4 dimensions. So there's some interesting connection here between division algebras, Lie algebras, and physics that was already known in that context. In some sense, extending to the magic squares isn't just an extension of that older work. Let me spend a moment looking at SO31. It's well known that you can think of SO31 in its spinor form as acting on 4 component vectors, written, however, as Hermitian 2x2 complex matrices, as shown at the top of this slide. You can think of that as just an expansion in terms of a basis of Pauli matrices, 4 Pauli matrices, 4-dimensional vector space, okay? And at the group level, the action then becomes conjugation by rotation matrices, boosts and rotations, which at the algebra level has the infinitesimal form shown on the right. In this language, which I expect many of you have seen, the rotations, and I'm a mathematician, the rotations are the infinitesimal generators, the Lie algebra elements are the infinitesimal rotations with no artificial factor of I added, unlike what most physicists do to get Hermitian operators. So the rotations at the Lie algebra level are always anti-Hermitian, but the boosts turn out to be Hermitian in this language. You have 6 A's, if you like, 6 matrices that act on these vectors, also written in terms of the Pauli matrices. Everything's written in terms of the Clifford algebra. The Clifford algebra is written in terms of the Pauli matrices. And they divide into these 2 categories. But that's not what we do. We're using the C prime row of the magic square. SO31 is parameterized by 2 division algebras. There's both a C and a C prime there. And what's been hidden from you all these years are the factors of capital L that you could stick in to these matrices without changing anything. Okay? But when you do that, the rotations and the boosts become anti-Hermitian, and you don't have the Pauli matrices themselves anymore. You have either I times the Pauli matrices for the rotations or L times the Pauli matrices for the boosts. So I've emphasized this transition both because I think you all know SO31, you're all used to thinking about some version of what I've just shown you. But this perspective is really important, that it is the split units that provide the unification that allow you to treat boosts and rotations and hence signature on an equal footing without getting involved in this Hermitian, anti-Hermitian, and a number of other related confusions. We think this provides clarification. Okay. All right, let me pause for a moment and see if there are questions at this point while I take a sip of my tea.
We could do this to the Dirac equation also, for example, write the Dirac equation using the split notation.
Absolutely, absolutely.
Thank you, thank you.
May I ask?
Jose.
Yes, please. So I noticed you had on your previous slide, you had an anti-commutator. Exactly. So there's an anti-commutator for the boosts, which now becomes a commutator. Is that
Exactly.
right?
Exactly. Okay. And again, that's the unification.
Okay, I see.
That's precisely the unification that's occurring. Yeah.
Okay, thank you.
And you expect that from thinking about the compact versions of the infinitesimal generators of the compact Lie groups, which are all rotations and all anti-Hermitian, and the Lie algebras all have commutators in them. They don't have anti-commutators in them.
Mm-hmm.
And again, this allows us to describe everything in that unified language.
I see. Thank you.
Okay. So the other thing that I wanted to show you, and I had a lovely demonstration that I was going to show you here, which I can't easily do here, is to emphasize that in Clifford algebra language, so all of these orthogonal groups have a Clifford algebra description, and in the Clifford algebra, you generate rotations by flips, by reflections. Two reflections about axes that are near each other generate a rotation in the plane of those two axes. Okay, and Corinne can actually demonstrate this with her fingers and pens. I'm not very good at it. I had an electronic demonstration I was going to show you, but the idea is if you do a flip, you do a rotation about an axis, and then you do a rotation about a different axis, you wind, a reflection, which is a 180-degree rotation, you wind up rotating in the plane of the two axes by twice the angle in between those two axes.
Mm-hmm.
And so the fundamental notion of rotation in a Clifford algebra framework is that you do two flips. Okay? And we forget that when we talk about rotations, because we're used to working over associative algebras where you can combine the two flips into a single operation, which is the rotation. But when you work over the octonions,
Mm-hmm.
okay, you lose associativity. And so it's not immediately obvious how to generate rotations as a single operation. And the short answer is you don't. You generate rotations as nested flips. In many cases, associativity will still hold, but in some cases it won't. Okay, so this idea of flips underlies what we call nesting. That in general, it takes two group elements in order to generate a particular rotation. And here it is worked out in general for any of the Lie algebras, any of the Lie groups in the 2x2 magic square. And it is this argument that Huerta, Kincaid, and I used to show that the nested flips are generating precisely the orthogonal groups in the 2x2 magic square, which therefore deserve the name SU2 K prime tensor K. All right. So the 2x2 magic square, the algebras are SU2 K prime tensor K. The generators of the algebra are anti-Hermitian matrices over the pair of division algebras K prime and K, and we've given labels to these, which I will emphasize Corinne will come back and use in more detail, I believe, in talking about the physics. But the message here is that you have anti-Hermitian diagonal matrices and anti-diagonal, off-diagonal matrices. These matrices are, in fact, not nested and anti-Hermitian, but that you have to include a set of nested transformations. And it was Rob Wilson who introduced this language of composition of circle of a new product, I circle J, to represent that nested operation as a single generalized matrix. Okay.
Mm-hmm.
All right. Well, the 3x3 magic square works the same way. I've given you all the pieces. I won't go through it in detail. The same construction tells you that the 3x3 magic square can be thought of as SU3 K prime tensor K. You get the obvious set of 3x3 matrices, generalizing the ones we had before. There's a new trace-free diagonal matrix. I'll tell you in a moment why it's crossed out. And there are, of course, 3 sets of off-diagonal matrices. And there's a set of nested matrices. But triality tells you that there's only one copy of SO8 when you get over the octonions, or SO44 if you're over the split octonions. And those correspond to the Ds, both the single index Ds and the double index nested Ds. And what happens is that triality tells you that you don't need the cyclically permuted versions of the Ds with the non-zero entries in different places on the diagonal.
Tevian, there's a question in the chat. Sorry to interrupt you.
No, go ahead.
Yeah, Hillary would like you to, could you please explain nesting once again?
Okay, so let me go back to nesting. Nesting is originally the fact that in order to do, for instance, an IJ rotation over the octonions, I have to instead of doing an IJ rotation, a rotation in the IJ plane, I have to do a flip about the I axis and then a flip about an axis in the IJ plane in order to make that rotation in the IJ plane. If I just multiply by K, that won't do an IJ rotation alone over the octonions. It will also rotate 2 other planes. And so there's no single matrix operation I can do to cause a octonionic 2x2 matrix rotation I can do that will cause a rotation just in the IJ plane. But there is a nested pair of, if you like, Clifford algebra transformations that will achieve that rotation. That's what nesting means originally. And then there is this notation to talk about those operations as or the generator of that operation as a single matrix, whereas under the hood, you're thinking about it as a composition of 2 matrix multiplications acting on something. Does that answer the chat question?
Yes, I would think so. We can come back for more discussion in the end. Yes,
Okay.
Hillary agrees, yes.
Tevian,
Yes.
you maybe make it a little bit clearer where you're talking about the Lie groups with nesting and where you're talking about the Lie algebras with the double index Ds.
Fine. So this slide about nesting is about the group. You can see it's got cinches and coshs and sines and cosines in it. To get the Lie algebra elements, you differentiate. Okay. When you differentiate, you still have nesting. But so M1 is a constant. It pulls through the differentiation, but M2 becomes an infinitesimal thing. And so both at the Lie algebra and at the Lie group level, you have nesting. When I've switched over to talking about these generators, I'm at the algebra level. Dij is standing for that nested infinitesimal generator of the pair of operations, the pair of flips that gets me the ij rotation.
Can you explain why the EPEQ squared is equal 1 and then -1 on the previous slide?
Well, I'm not sure where we are. Oh, here. Okay,
Yeah.
I'm sorry. So I blew through that too fast. This is Clifford algebra language. The EPs and EQs are the unit generators of the Clifford algebra. Okay, so they're my coordinates, if you will. And you can think of them as gamma matrices equivalently. And in signature 3-1, for instance, some of the gammas will square to +1 and some of the gammas will square to -1. When you now try and do a rotation in the PQ plane, it might be a rotation and it might be a boost, depending on whether the two directions have the same character or opposite characters. So whether the individual gammas square to +1 or -1. And so
Okay.
that parenthetical comment is, if it's a boost, you use this line, the first line. If it's a boost, you use this first line. And if it's a rotation, you use the second line.
Thank you.
Okay. All right, I was talking about triality. The SO8 transformations are on the diagonal. They're not the X's, Y's, and Z's. And triality tells us that we have 3 sets of diagonal matrices, essentially depending on whether you put the 0 in the 1-1, the 2-2, or the 3-3 slot. And what triality tells us is that those 3 copies of SO8 are the same, literally the same. Of course, you have to map one basis onto the other basis, which can be complicated. But as an algebra, they are exactly the same algebra. And so if I want to think about E8, which is the most interesting case in the magic square, I will have 2 SO8s, one coming from O, and the other really in SO44 coming from O prime. But in each case, triality tells me that I don't need to include all 3 sets of diagonal matrices. It's enough to include just the D's or just one of the other versions. We've broken the symmetry by picking the D's. The short version of Rob's description of E8 is that, first of all, E8, you have to work in the adjoint representation. Nesting is problematic. You can't nest operations acting on some representation and then just work out the composition of matrix multiplication. You have to be able to act on elements of E8 itself, some of which are nested. And so it's not enough to have a nested action, nested operations. You need to be able to act on nested things. And again, what Rob showed, what's in our paper, is that if you represent those nested things in terms of these generalized matrices, and if you use a natural multiplication of nested elements, that you can represent indeed the full Lie algebra E8 in terms of these 3x3 generalized matrices and ordinary commutators, with a couple of extra rules that tell you how to deal with the nested elements. There's one warning that I need to shout from the rooftops, which is that if you want to take commutators of nested elements, you must always do so using a preferred representation in triality. So using just D's, for instance, not one of the other forms. You can't mix and match. So there's a subtlety that for today I will sweep under the rug. But the short version is, if you use the right notation, you can indeed write E8 as 3x3 anti-Hermitian matrices over O prime tensor O. Okay. Next guiding principle. I spent time talking about the 2x2 magic square. And that's because, of course, 2x2 matrices sit inside 3x3 matrices. And we want to argue that that split is fundamental. So we are going to break the symmetry. Of course, there are many ways that you can embed the 2x2 magic square, the groups in the 2x2 magic square, in the corresponding groups in the 3x3 magic square. We're going to pick a particular way to do it. And so we will, as you saw on the previous slide with D's, we will preference the upper left 2x2 block, and we will think of a 3x3 matrix as being divided into a 2x2 piece, a 1x1 piece, and a 2-component column. And we've used language like this in the past to describe E6 and the action of E6 on the Alegbra algebra. And I want to emphasize that what you're doing here is you're effectively splitting up, you're combining, in that E6 case, you're combining a vector representation of, in the E6 case, SO91, with a spinor representation of SO91 into a single Albert algebra element. You're acting on them with a matrix representation of E6 in the standard form, P goes to MPM dagger, and that single operation correctly induces both the vector transformation on the SO91 vector and the spinor transformation on the SO91 spinor. And so what you're getting in that E6 context is a unified description of the vector and spinor actions at the same time. We're going to take that principle and apply it not just to E6 and SO91 and Lorentz spinors in 10 dimensions, but we're going to apply it everywhere in the magic square, where we should be a little bit careful to talk about adjoint representations in the upper left. But we're now going to think of E8 acting on itself, but E8 is split into an upper left piece, an upper right piece, and in fact, that's it. Because of triality, you don't need to look at that bottom piece. Okay, so if you do that, E8 splits up into two pieces, the 2x2 piece, which we'll call the adjoint sector, the 2x1 piece, which are spinors, And that 2x2 piece in the signature that we're in is a representation, are the generators for SO12-4. That's the 2x2 Lie algebra in the bottom right corner of the magic square. And so we obtain a representation of SO12-4. And if you're paying attention to my labels, generated by the 2x2 matrices, which were X's and D's. And you get 128 remaining pieces, the Y's and the Z's, which are two-component octonionic spinners, which is precisely a single vial spinner representation of SO12-4. So we haven't said anything that folks in representation theory don't already know. E8 decomposes into SO12-4 and a vial spinner representation, 128 of SO12-4, but here it is explicitly in terms of octonions. Okay. All right. So now the game is, what can you do with SO12-4? Okay. And SO12-4 is pretty big. You can do all kinds of things with it. Here's what a comment I made a moment ago, that E8 in this signature splits into SO12-4 plus a spinner rep of SO12-4. And of course, key point, I can break SO12-4 further into anything I want that sits inside SO12-4, and the spinners will also then break up into spinner reps if I picked orthogonal groups, but into reps of whatever those subalgebras are. Okay. And so the idea that Corinne will then utilize to get a grand unified theory is that SO12-4 is just big enough to contain SO31, a real form of SU3, SU2, U1, and a complex structure. That this algebra is exactly the right size, and the spinners are exactly the right size to get you a version of an SO10 or SU5 grand unified theory together with its spinners. Okay? That's not what I want to talk about today. But I want to emphasize that this is our third principle. It's not merely that you use E8 as a symmetry group. It's not merely that you use E8 to represent particle states. It's that you do both. You find within E8 both the symmetry group that you want for your grand unified theory and the particle states on which it acts. And here's the comment I made before. I'll talk my way through it one more time. SO12-4 contains precisely the Lorentz group. If you're doing an SO10 theory, both a left and a right-handed weak group, a color group, an E&M group, and two dimensions left over that you can use to make complex spinners. Remember, we're working in real Lie algebras, and so you have to do something extra in order to get the complex spinners that you see in standard particle physics. And that complex structure also comes out of E8. Everything comes out of E8. Okay. As an aside, if this turns out to be an appropriate framework for a grand unified theory, there's not a lot of wiggle room here. It's either right or it's wrong. And in particular, there's only room for 4 space-time dimensions. Okay. Let me move on to the final part of the talk, which is to talk about a different subalgebra of E8, namely E6, and its minimal representation, the Albert algebra. So again, when you break up E8, you know you can get an E6 subalgebra. The extra pieces have to be representations of that E6 subalgebra, and the only game in town is the Albert algebra. So you're going to get the Albert algebra for free sitting inside E8. Here's the decomposition. It's well known, even in the signature. The centralizer of E6 in E8, the centralizer is the algebra that commutes with, the maximal algebra that commutes with E6 is SU3. In this signature, SU3 is real, so it looks like SL3R, but this is really E6 plus SU3. And yes, in our grand unified theory, that's the SU3 of color. Okay. And what you wind up getting left over are 6 27s. The 6s are reps of the SL3R, and the 27s are Albert algebras, Jordan matrices. So you have 6 copies of the Albert algebra using language from the grand unified model. You get 6 colored Albert algebras. Whether you want to interpret the SU3 as color may depend on what you're doing. For us, they're color labels. Okay. Getting those color labels right requires, again, that we're over the split octonions, where we can make real eigenvalues. SU3, of course, has only imaginary eigenvalues, but SL3R has real eigenvalues. Okay. And so we need to use those null elements, which I've written out here explicitly, I plus and minus IL, etc., as these 6 labels, 3 and a 3 bar labels for the Albert algebras. This work is in a paper that I just posted to the archive. Unfortunately, with technical difficulties, missed the deadline, so it didn't appear this morning. It should appear Monday, but there should be an archive posting with a title, with this title, showing up on the archive on Monday. If you can't track it down, let me know and I'll mail you a copy. Each of those 27s must, from representation theory, be an Albert algebra. But what we've done is we've converted the Hermitian matrices in the Albert algebra to anti-Hermitian elements of E8 by multiplying by a split octonionic unit, just as we did way back when for SO31. So we have a copy of the Albert algebra in terms of anti-Hermitian matrices sitting inside E8. All right, that's not the whole story. There's a subtlety. You should be asking yourself, what about the identity matrix? The identity matrix is in the Albert algebra, but no multiple of the identity matrix is in E8. And the answer, again, is nesting. That there are nested elements in E8 that indeed are imaginary multiples of the identity. And so you can find elements of G2, elements of SO8, SO44, I should say, to play the role of those identity elements in the Albert algebra. So that's the subtlety that makes this work challenging. Again, details are in this paper. I won't bore you with those details here, except to say that it does work out. Okay. All right. But you can actually do more. There are subalgebras of the split octonions, unlike the octonions. The split octonions admit a large number of subalgebras. They're all weird, okay?
Tevian, can you hear us? The screen froze. I think we lost the voice, Tevian. Can others hear me?
Yes, I can.
Okay, so my end seems okay. Looks like we've lost Tevian's voice. Tevian, you want to log out and log in again, maybe? The slide. Okay, Tevian might be logging in again. Yeah, so hopefully Tevian will log in again. Yeah, back, yes. Yeah. Can you hear us, Tevian?
Yes, can you hear me now?
Yes, yes. Please go ahead. Please go ahead.
All right, I'm very sorry. I don't know where I cut out.
Right.
We are in this slide, yes.
All right, so let me start with the slide again. Okay. So there are non-trivial subalgebras of the split octonions, unlike the ordinary octonions. And I've shown you actually two of them here, reading either the top signs or the bottom signs. These are two three-dimensional subalgebras. I plus IL times J plus JL is K minus KL. And that's the only non-zero product of those three elements. So these are very weird, very degenerate subalgebras. Nonetheless, they close. Okay. What that allows us to do is to not only implement the Albert algebras as vector spaces, as representations of E6 within E8, but we can actually reproduce the algebra structure of the Albert algebra, the products, the Jordan product and the Freudenthal product, in terms of commutators in E8. Okay? So here's the structure. The Albert algebra has a so-called Jordan product, unfortunately normally written with a circle. That circle has nothing to do with the nesting circle we used earlier. It has a Freudenthal product, which is something more complicated, and it has a determinant. And rather than emphasizing the details of those products, what you want to think about is that the trace of the Jordan product is a dot product, and the Freudenthal product is a cross product. And there's a very natural sense in which those two products generalize the traditional dot and cross products in Euclidean 3 dimensions. So to make a long story short, if you take elements X and Y are elements of a Jordan standard Hermitian, come on, won't. There we go. If you take X and Y, standard Hermitian elements of the Albert algebra, and you multiply them with these split octonionic labels, and then you take commutators. The labels multiply according to those three-dimensional algebras I just showed you. And the remaining piece of the commutator, depending on which elements you pick, whether you pair plus with minus or plus with plus, you either get the trace of the Jordan product or the Freudenthal product represented within E8. Those results are in a second paper that's in preparation. We don't have that quite ready to share yet, but those details will also be available soon. But I can tell you the idea from representation theory, which says that this had to be the case. Okay. And again, this is a quick overview of some fairly subtle representation theory arguments. But E8 also splits into E7 and SU2 as opposed to E6 and SU3. And what happens when you do that is that you had 6 Albert algebras. 2 of them go into E7, and the remaining 4 go into 2 56s, the minimal representation of E7. So again, E7 has some Albert algebras in it, E6 plus Albert algebras, and these representations of E7 have some Albert algebras in it. Okay? But the action of E7 on the 56s, as was shown by Freudenthal miraculously back in the 60s and 70s, the action of E7 on the 56s involves Freudenthal and Jordan product. It's a mess, but it involves Freudenthal and Jordan products. And so the fact that E7 must act on 56 in E8 means that that action must in fact implement both the Freudenthal product and the Jordan product. So this page is the theory that tells you that the calculation I'm presenting on this page had to be true. And both that theory and the practice, again, are in this paper that hasn't quite come out. All right. Well, I'm pretty much done. Let me summarize. I'll start at the bottom. First of all, I may have miscited the papers before. We had 2 papers last year. The JMath Phys paper that I referred to earlier is actually the physics paper. That one's out, and that's the one Corinne will be talking about in a month. The other paper, we've returned the proofs, but it hasn't come out yet, is available on the archive, and the number is there if you want to look it up. The E6 and E7 papers are not quite publicly available yet, but the E6 paper should be out on Monday on the archive. And now let me talk my way through the summary and then open the floor for discussion. So first of all, 3 key guiding principles that led us down this path. The first one is look at real forms of Lie algebras, not complexified forms, to allow us to cope with the signature. Miraculously, we nonetheless have the ability to talk about complex spinors without ever leaving those real Lie algebras. So we get everything we want sticking to real Lie algebras. Second, the 3x3 structure that E8 has breaks naturally into a 2x2 and a 3x3, a 2x2 structure and a representation structure, which allows our third conclusion, not only the symmetries, but also the representations should live in E8. E8 is in some sense the largest element of its algebraic category, and it is, we think, miraculously just the right size to accommodate at least a candidate description of fundamental particles. All right, more specific details. E8 splits into SO12-4 plus spinors. That allows a particular gut. That gut is something Corinne will talk about next time, which contains the standard model gut. It contains the Lorentz-Lie algebra, and it contains the building block for a complex structure. But I've also shown you that if you're interested in E6 and Albert algebras, or for that matter, E7, E8 is also a natural arena to study those properties because you get both the group and the representation in a unified picture. I will stop there. Thank you very much. My apologies again for the technological issues I had at the beginning.
Great. Thank you so much, Tevian, for a beautiful lecture. There's lots to be absorbed and understood. We also look forward to the recording, which is a treasure house. We go back and refer to it. Michael, you want to add something?
I honestly don't think so, Tevian. Again, it was a wonderful talk, immensely rich. I particularly like the take-home message about that. It's all already there in the reels.
Yeah.
Okay, I mean, I'm sorry, I don't want to put words in your mouth. No, I really enjoyed it enormously. Thank you very much. I'm looking forward to what I hope is going to be a very rich discussion as well.
Yeah, so the talk is open for questions. Kindly
Let me comment. Let me reply briefly to Michael's comment about the reels, which is one of the first problems that one has the minute one wishes to study quaternions or octonions and apply them to physics, is trying to figure out in standard quantum mechanics, say, what the heck I is. Which I is it? And so from this point of view, we're actually claiming it's none of the above, that you have the octonions, you have the split octonions, and separately you have something which is the complex structure. But at least we're providing a language that allows you to discuss that question.
Yes, absolutely. And what you just said about the problem you confront at the very beginning as to how the quaternions particularly fit in the sort of structure is it's so very, very close to some of the things which I've been discussing in the last couple of months with Basil Hiley. I think I don't think he's actually in the audience for this talk, but I'm going to make very sure indeed that he does watch the recording, because I think he'll find himself in very, very warm agreement with many of the things that you've been saying, and hopefully we can put one of the two of you together in touch and see if you can bounce some of these ideas off one another.
We'd be delighted. We would look forward to that.
Okay, thanks again. A fantastic talk. Now let me shut up and let people take the floor and ask their questions.
Okay, go ahead, please. Questions are very welcome.
Could I ask a question? This is Anthony Lazenby here.
Yeah,
Yes,
please
Anthony.
go ahead. Please go ahead.
Hi, thanks, Tevian, very much. Very interesting talk. I just wanted to continue on that question about the complex structure, because you emphasized how you initially didn't want the complex structure so that we had proper account of which are boosts and which are rotations. So I wasn't quite clear why later on you were keen to use this final SO2 bit that you got in order to build up a complex structure. Could you say a bit more about that?
Okay, so let me see if I have it on an early slide. No, it's gone. Come back to the very end. Sorry about that. Okay, so here. So if you count the number of dimensions, well, let me start at the end. When we describe a gut, so again, this is something Corinne's going to talk more about, we're going to want to be able to talk about things like weak eigenstates or spin eigenstates. And when we do that, we're going to have a spin operator, which is a rotation. It's anti-Hermitian. But in order to talk about eigenvalues, we're going to wind up with imaginary eigenvalues. Again, we've just worked really hard to make everything in E8 anti-Hermitian. So everything has imaginary eigenvalues if you're okay. But that doesn't touch base with real physics. So somewhere along the line, we have to be able to talk about complex spinor states with complex eigenvalues. And it's that I that we're trying to eventually get at.
Tevian, can I jump in here?
Please, Corinne.
Yeah, so when people take a Lie group and then they look at the infinitesimal things, they find the Lie algebra, the sort of knee-jerk reaction is to complexify that. But when you complexify the Lie algebra, you lose the connection to the original Lie group. What we're saying here is we want to take E8, find the Lie algebra for that, and not complexify at that stage. But once we start breaking E8, we find the complex structure as an element within E8 itself. And that complex structure then acts on the representations, there's these spinor representations that are inside E8 without ever complexifying the original Lie algebra. So we get complex spinors without ever complexifying E8 itself. Does that help?
Yeah, okay, thanks.
Anthony, let me give you an example that might help. I'm sorry, without the technology I'm used to, I can't write this down. But just as E8 breaks up into SO16 plus 128, so SO12-4 plus 128, that 128 is a Majorana-Weil spinor, so it's a real spinor. But you could have broken into SO14 plus an SO2, and it's still, you get 128, but it's now a Weil spinor of SO14. Weil spinors are complex. They need to have some sort of complex structure. The SO2 that's left over actually provides that complex structure. It all comes out automatically. You get the right kind of spinors for whichever subgroups of SO12-4 you want to look at. If they need to be Weil spinors, the I is also there in E8.
Okay.
Thank you. Tevian, while we are at this slide, could I ask, how do you physics-wise propose to interpret the weak right SU2R?
I really should leave that for Corinne. It is interesting. So there's no there's no question that if you start from SO12-4, it's there somewhere. Okay. I will point out that one of the things that Corinne is going to show you next time is that as you wander through the magic square, the natural path does not treat SU2 left and SU2 right equivalently. One of them shows up before the other. And that's a triality issue. Okay, that when before you get to the octonions, you need to look at 3-3 components. But after you get to the octonions, you don't. And so there's actually some peculiarity, some mathematical structure to the magic square that allows you to distinguish between SU2 left and SU2 right. That's a mathy answer.
Mhm.
How we interpret that and so forth, unless Corinne wants to say something now, I would ask you to wait until her talk.
Okay, Corinne, up to you. You want to add something?
No, I think it's a little complicated to try and describe right now.
Okay,
But
thanks.
it's a great question, and let's talk about it in a few weeks.
Great, thank you, thank you. Veselin, please go ahead.
Hi. I also would like to join the other participants and thank you for this wonderful presentation. And please excuse me my unfamiliarity with the magic square, but can we go back at the first slides and can you explain how should we think about the column and the rows? Is that like by modules or?
This one?
Yeah.
Okay. So the base, let's see if I can find, let me try a different one actually. See if,
Maybe with the split algebras is even better because then we can
Yes,
replace the
yes,
split algebra.
yes.
Yeah.
Okay. So the idea is that we're used to writing that first row as SU3R, SU3C, SU3H, and actually SU3O for F4. But if you instead look at the first column is better written as SU3R, SU3C prime, SU3H prime, SU3O prime. People are not used to using the split algebras as parameters, but they should be. The point is that every single algebra in this table is an SU3, but it's an SU3 over the tensor product of two division algebras. One from the left, R prime, C prime, H prime, O prime, and one from the right, R, C, H, O. So for instance, SL3R is really SU3 C prime tensor C. Okay. The two caveats are you don't see the factors of R. So the first row and first column, you don't really need to write the R's. And R prime is, of course, the same thing as R. There's no such thing as the split reals.
Okay, so if I understood correctly, then if I take elements and in a column, then I can treat this element as algebra over the field that is on top of the column. And it's reflected in the labels already in there. But then depending on which row I take, I would consider that there is a product also with this division
That's
algebra
correct.
on
That's
additional.
correct.
Okay.
That's correct. It's the
Okay.
tensor
Tevian?
product. Yes, go ahead.
Tevian, I think it might help to think about pick an element in the square. It's labeled by something in the split octonions and something in the octonions. Take the tensor product of those two spaces and then build all the anti-Hermitian 3x3 matrices that you can with elements in that tensor product space. And that's the that's the algebra that you're working with.
So
Yes,
what
that was kind of the original idea. I was thinking about it, but then I'm confused. How does it kind of landing back to whatever was the column label?
You use the row and the column, the tensor product of the thing in the row and the thing in the column to be the elements of your 3x3 matrices.
No, let me comment here. The names on this page are the traditional names.
Mhm.
And traditionally, people didn't stick in the split label. And so they had to have a different name for the first row, for the second row, for the third row, and for the fourth row.
Mhm.
We're saying that there's a different way to name these 16 things, not the names here.
Okay,
That
I
would,
see.
that would write them all as SU3 over the single algebra K prime tensor K. Every
see.
one of those 16 things.
Okay,
And that
thank you. Yeah.
yeah.
So following what you said a few moments ago, E8 is SU3O tensor O prime.
Yes.
Okay, yes, thank you, thank you. So I wanted to ask, I was curious, it was very interesting to see E7. Usually we talk about E6 and E8. E7 sort of gets neglected. Would you or Corinne say something about the physics of E7 from
Well,
the
I can
standpoint?
say something. I can say something quickly, which is that so E8 is sitting here in the bottom corner of the magic square. And for each of the other elements of the magic square, they're of course subalgebras.
Mm-hmm.
Every time you have a subalgebra, you can ask, what is the centralizer? Okay. And so each of these has, if you will, it's a terrible word in this context, a dual, a centralizer, another piece. When you go E6 to E8,
Mm-hmm.
the centralizer is SU3.
Mm-hmm.
Okay. We would argue that's color.
Mm-hmm.
But when you go E7, notice I picked an E7 in a different place
Mm-hmm. Mm-hmm.
to E8,
Mm-hmm.
the centralizer is SU2.
Okay.
Okay, well, there's your weak force.
Mm-hmm.
And so there's a transition from here
Mm-hmm.
to here
Mm-hmm.
that involves both adding an SU2 and adding an SU3.
Yeah, thank you. Yeah, very nice. Yes, yes. Mm-hmm. And when you have 6 color labels, what am I to make of it? Because for QCD, I need just 3, right?
Three colors and 3 anti-colors. I skipped over that. It's a
Okay,
3 and a
okay,
3 bar.
Okay,
It's a
okay. Sorry. Okay. Yes. Yeah. More questions, please.
I should really have written not 6 times 27, but 3 times 27 plus 3 bar times 27 bar.
Sorry. My confusion. Sorry.
Yeah.
Yes. Also, is there some way to relate the octonionic projective plane OP2 to the magic square? Does that question make sense?
Absolutely. The magic square, the OP2 is a subset of the Albert algebra. Okay.
Yes. Yes.
So you can think of the points of OP2 as what we call one squares. The elements whose Freudenthal square is 0, whose cross product with itself vanishes. And there's a whole language you can make where the points are the 1 squares, the lines are the 2 squares. So it's a matter of how many non-zero eigenvalues they have.
Mm-hmm.
And you can use Jordan and Freudenthal products to define incidence relationships. And that's in our book, and I think it's in one of our papers.
So again, that is again contained in E8 from your point of
Yes, it's an interesting question. I've not actually thought about whether these operations can actually be used to talk about incidence in the octonionic projective plane using E8 operations alone. I suspect the answer must be yes, but I've never looked at it.
Thank you. Thank you.
Could I ask another question?
Yeah, please, please.
So you're using split Octonians, and you've got a fairly complex, that's not the wrong word, additional algebra, which you have with the L's and the I's and the J's and so on. And I was wondering, does this sort of diminish the argument for why we could be interested in Octonians in the standard model, in the sense that they are absolutely put out as the last division algebra? The split Octonians are not a division algebra, and you've introduced this additional algebra. Where should we think of the sort of arguments for why these should be fundamental structures? Where does that come from?
So I think, I'm not sure that I see a negative in anything that you said. The Octonians and the split Octonians are sort of the largest of the reasonable, I don't know what word to use, composition algebras. The magic square requires two division algebras. Signature controls whether you want to use the regular division algebra version or the split version, but I think of those as equivalently at the top of their category. The magic square describes the exceptional E algebras, and the OO version is the biggest. Whether you do OO, OO prime, or O prime, O prime, that's controlled by physics. But those three objects are, in my mind, the only candidates for biggest natural algebraic object here.
I could make an argument that that could be the Sidonians, because they similarly are, you know, they come by the Cayley-Dickson procedure.
They have zero divisors.
And they have zero divisors, which you have.
No, there's a difference.
You know, you pay your money and you make your choice.
Yes. Let me rephrase. Yes, maybe. There's no question that beauty is in the eye of the beholder, and that one could impose a standard of beauty that would lead to the Sidonians. Okay. The split Octonians are a composition algebra. You cannot have the product of two elements have magnitude 0 unless one of the factors has magnitude 0. The Sidonians do not have that property.
No, I agree.
Okay, and so that's my standard of beauty, but I agree that you could challenge it.
Yes, but they have, you both have ideals, let's put it that way, which are an integral part of what you do, of course.
Yes, yes.
Yeah.
I don't know what to do with degenerate algebras. I showed you one instance where it's helpful, but the cases where the inner product is actually degenerate, and I mean SO44 I know how to deal with, but a degenerate product, I lose touch with my own geometric intuition.
Right.
Thank
So
you. Excellent.
since
Go ahead.
we were talking about the beauty in the beholder, I mean, usually we will try to kind of touch with observations in nature, which brings into physics. And to me, kind of a question that I wasn't able to understand is basically how to think about this different complex I, J, and K if I use the algebra. Probably as idea like you pointed out with the rotations as nested compositions could be interesting thing, because then it's very much like parity operations, but still kind of not clear to me how do we relate this with the specific observabilities.
The
And
last
going
line was
further,
could you repeat, please? The last line was lost.
I was saying that in a sense, they're kind of like parity operations, but the parity is easier to understand in regular space. But understanding what is the equivalent of I, J, or K kind of operations in this other space, what would be the physical meaning is kind of difficult for me to land on. And I don't know if you thought about it or if you have some comments about this.
So again, that's a good question to ask Corinne in next month. We are attempting here to present a theory that has both Lorentz degrees of freedom and internal degrees of freedom, sort of in the same framework. And so symmetries include both physical rotations and SU3 color transformations. And so some of the labels, some of the coordinates, some of the directions, if you will, are talking about things like color and weak eigenstate. And some of them are talking about more a physical orientation like spin. And I think you're asking, how do you combine, how do you reconcile physical rotations with sort of internal rotations? I don't have a better answer for you than to say some of them are physical and some of them are internal.
From a larger space-time point of view, internal and the usual rotations, this sort of all get together, no?
Well, I will say one thing here, which is that first of all, we start with E8. We think E8 is fundamental. Okay. Until you break the symmetry, you don't know which directions are which.
Absolutely.
Our model's actually in momentum space. And again, this is a sort of vague idea. I don't have a way to make this very precise. But to go back and forth between momentum space and position space requires a Fourier transform. Fourier transform requires a preferred complex structure. We don't have that preferred complex structure until after we've broken the symmetry. Okay. So even though we have a theory that you could think of as living in 16 dimensions with 4 time coordinates and 12 space coordinates, it's not until after the symmetry is broken that we can identify space and time position. And so maybe this is one of those questions you're not supposed to ask, right? That the theory doesn't allow you to ask that question until after the symmetry's been broken, at which point you only have 4 direct dimensions left and they are ordinary space-time. That's very speculative, but that is a possible consequence of what we're doing.
But to me, I think that's very reasonable, because only then you can talk of space-time and internal, only after the symmetry is broken, yes. Before that, whatever you have is whatever you have. We have to interpret it for what it is.
Right. I mean, this is sort of the opposite of the sort of kind of string theory interpretation,
Yes.
where you have physical rolled up dimensions that you don't see. We're arguing do things in a different order, and it all hinges on the fact that until you figure out what I is, you can't do anything with the complexes. So no Fourier transforms, no Weil spinners. You don't have any of those things until after you've figured out what the complex structure is.
And you are not curling up any dimensions.
No.
That's very important, I think, because all the string theory problems come from curling up. Yeah. So I had I wanted to ask you something. Right. So with one E8 in this 128th spinners, you get all the chiral fermions left-handed as well as right-handed, is it?
We believe so, and we even have a construction that Corinne will talk about as to how to fit in 3 generations.
Yeah. So I someday I want to understand why I need 2 E8s, E8 cross E8. Why you need only one? I will try to. You have any thoughts on that?
I do not. So we, at the moment, we're looking at just one. Back to Anthony's topic of beauty and naturalness, there is one larger structure that could come into play here, which is the leech lattice. So there are, you know, you pays your money, you take your choice.
Yeah.
We are enamored at the moment with a theory involving a single E8, but I agree that Sedanians, E8 cross E8, leech lattice, there's room to tweak things a little bit if this should turn out not to be sufficient. We're putting our money on small is beautiful.
No, I agree. This should be done. It's beautiful, undoubtedly. Yeah, I'm just trying to understand where are we going in different directions. So I'm claiming, I mean, I could be wrong, that if I have 2 E8s, I will have gravity coming in. And somehow, in my way of looking at things, when I want chiral fermions, I naturally want 2 E8s. But I mean, what you do also could be definitely, of course, right. We have to someday try to see how these things compare. Yeah.
So as you know, Tejinder, both Corinne and I started off in relativity and applications of relativity. So
Right.
gravity is near and dear to our hearts.
Right.
But I have to say that we would argue that there is no gravity in such a theory, nor is there room for it. Now, I know that many people, including you and our collaborator, Rob Wilson, would disagree. So this is you know, let's call it an open issue.
Yeah.
But
That's why sorry, go ahead. Please finish.
our intuition is that gravity is different and needs some other mechanism.
Okay.
Can I make a comment on that?
Yeah, please.
So, of course, there's a famous predecessor for this work on E8 and the standard model in the form of the Garrett-Lisi approach. And in that, he believed he had incorporated gravity. And that basically comes, if I can put it this way, that in your terms, you end up with an SO31. And you can talk about, maybe after the symmetry breaking, you can talk about actual rotations in space-time. And as soon as you've got rotations in space-time, you've got at least half the way to gravity, because gauging those locally gives you, the connection of gravity. And what Garrett-Lisi said was he was adopting the McDowell-Mansouri version of ordinary gravity, which basically only needs a connection. It doesn't need the diffeomorphism. Now, I don't really understand that myself, but I'm just wondering if you looked at the question of whether with what you've got already, the SO31 and local gauging of that, you're basically almost at gravity.
So I will say that you are echoing thoughts we've had over many, many years, which is that the gravity structure, if it's going to come out of this approach, is going to come out of some sort of local gauging of that SO31 symmetry. I agree with that completely. The issue, I remind you, is that since we're in momentum space, we don't know how to gauge. And so I agree with you that that's a plausible direction to go, but we don't know how to do it.
Well, let me ask a stupid question then. Did Garrett Leasy get that bit completely wrong? Because he thought he could get gravity via essentially just writing down the pieces of the connection.
I don't know how to answer that question.
Right.
What I remember reading as a criticism of Garrett Leasy, there was this thing that he couldn't get chiral fermions out from his E8. That's what I remember as one of the principles.
So people have harped on his counting of fermions. I don't know to what extent people have discussed his treatment of gravity.
Right.
Yeah, so that's why, Tevian, I have eyes on the weak right, SU2R, keeping also in mind, a lot of literature that gravity and the weak force are related. They have the same dimensional constants. So I have a lot of interest in SU2R being related to weak gravity, to gravity. That's why I asked, what do you propose to do with the SU2R? So I'll wait for Corinne's talk. Because if Peter Voigt recently had a paper on Euclidean twistor quantization, where he uses on a Euclidean signature the SU2R and the self-dual part of the connection to derive Einstein gravity from SU2R. So you don't need both the anti-self-dual and the self-dual part of the connection. One half is good enough.
So this sounds more along the lines of some avenues that our collaborator Rob Wilson has been pursuing.
Mm-hmm.
I can only repeat that certainly my belief, and I'll leave Corinne to speak for herself, is that there is not room for gravity within E8, and that I for one am not eager to see the SU2 right used for that purpose. Even
with E8 cross E8, you might not see gravity, you're saying?
I don't know how I don't know how to answer that, because I'm not yet sure what you accomplish with the E8 cross E8.
Mm-hmm. So
there's a lot
is essential for getting chiral fermions and for bringing in gravity. And also, very importantly, the only way I know how to use the Albert algebra to calculate mass ratios is to work with E8 cross E8. That's a must, yeah. Okay. Anyway, so we can discuss this later.
All of these are interesting avenues. All I can do is speculate.
Thank you. More questions, please. So, Michael, you want to add something?
I'm just overwhelmed by the quality of the discussion. No, I don't think I have anything to add. Thanks. I'm revolving some very strong resonances of discussions that I've been having recently with Basil Hiley, in the light of what's just been said. But no, I think I have nothing to add. Thank you very much, though, to everybody who's contributed. Obviously, Tevian above all, but to everybody who's taken part in the discussion too.
I second that sentiment, Michael. Thank you.
Yeah, it was wonderful. We love the talks and the recordings, because the recordings are a treasure. It's our collection, Michael and I.
Yes, it's gradually building up into, I think, a really valuable archive, which I hope is going to be expanded. In fact, with a couple of parallel discussion groups, which we're hoping to launch in the next 3 or 4 months. I'm
tempted, Tevian, just since we have a few more minutes. Suppose I asked you, what is the relation between the Dirac equation and the quaternions? Would you like to put it in your way? I'm curious if you can say something on this.
So we originally proposed in a formalism that was at that time over E6, that if you had took So points in the projective plane, to come back to the language you used earlier, which you can think of as as quaternionic column vectors living inside the octonions. That if you square such a column, so you turn it, you take its outer square and turn it into a 3x3 Hermitian matrix, it yields both a momentum vector and a spinner. And furthermore, that pair satisfies the Dirac equation. Okay, that momentum is the momentum that comes out of the Dirac equation, or goes in if you prefer. And so that solutions of the Dirac equation are precisely these one squares, these elements of the Jordan algebra, these points in the octonionic projective plane. That language translates into E8 as certain commutators. And so we are able to write down, and this again is what Corinne will be talking about, eigenstates of the various standard model symmetry groups at rest, together with their momenta and a corresponding Dirac equation. That much we can do. The challenge that we haven't yet succeeded in meeting is to add the connection that yields interactions within E8. That's the big piece that we're stuck on.
Interactions?
Yeah, we sort of know how to do it, but we can't quite get it to work nicely.
Yeah. So the reason I asked you is that there seems to be a rather deep connection between the Dirac equation and the quaternions. So from the physics point of view, it is very natural to ask that if we generalize the quaternions to the octonions, that implies a Dirac equation. What is its physical content? And that's where we learn that if you describe elementary particles using the octonionic Dirac equation, you learn more about the standard model than you knew using the quaternionic Dirac equation.
Yes and no. I will warn you or remind you of one of the unexpected consequences, unexpected to us, of our old E6 Jordan algebra stepping stone to this work that we're doing now, which was that the Dirac equation solutions were elements of the Jordan algebra whose Freudenthal product vanishes. And even though you start off over the octonions, all of those solutions are quaternionic.
That part I remember, but like, the eigenvalue equation that you wrote down for the exceptional Jordan algebra, when I find its eigenvalues using octonionic spinner descriptions of quarks and leptons, those eigenvalues I have some information that I'm seeing for the first time. Maybe it's all quaternionic. Maybe it's all quaternionic.
Depends which eigenvalue.
Sorry.
Again, it depends which eigenvalue problem you use. If you're using the Jordan eigenvalue problem or the straight up octonionic eigenvalue problem, there's
it's the Jordan eigenvalue problem.
You have to state carefully which eigenvalue problem which equation you're solving. I don't remember which one you chose.
The cubic equation, which depends on the trace, the determinant, and the two form. This cubic equation is the eigenvalue equation for the exceptional.
3 eigenvalues or 6 eigenvalues?
Three eigenvalues, three
they're-
real eigenvalues.
And they're real. Yeah. Okay. So you're doing the Jordan eigenvalue problem. Okay.
Yes, three real eigenvalues.
Yeah. No, that's probably the right one. Where you only get three real eigenvalues.
Yes. And when I work out those eigenvalues using, say, Cole's construction for spinors from the Clifford algebra, those are very simple and neat eigenvalues, which I have never seen before. One of the eigenvalues is straight away the electric charge, but there are two other eigenvalues, and these have meaning.
I can't comment on that. I don't know the answer.
Yeah.
I think what I would like to know is how to relate the operators you're using, whose eigenvalues you're computing, how to relate those operators to elements of E8 would be the question I would want to ask.
Yeah, so there's very clear relation with E6, and E6 is sort of like SU3 cross E8 is SU3 cross E6.
Right.
So for me, that SU3 actually goes to make spacetime. When I have two copies of E8, I use SU3 cross SU3 to make a higher dimensional spacetime, from which I have to recover SO31.
No, but it's enough to take it from E6. If I
Yes.
So I want to compare your E6 elements with our SO12-4
Yes.
to
Yeah.
get a handle on what I think you're computing. And I've never done that.
Fair enough. Yes. I have not thought in the language of SO12-4. That's a good point. Yes.
But I will remind you that for us, because we are trying to fit the spinners into E8 as well,
Mhm.
the symmetries all live in the upper left 2x2 block. They all live in SO12-4. Okay. So you can go down to SO9-1 if you want to do E6. But the operators that we study are not 3x3 objects, they're 2x2 objects. And that may make a difference. That may even be an irreconcilable difference between your approach and ours.
Looks like, seems so. Yes, I would need 3x3 matrices. Yes.
Yeah. Because
Tevian?
go
Tevian,
ahead. Yeah.
I will remind you that E6 has spinners in it.
That's my-
Our SU2 right is broken.
Yes.
And I think that's relevant to the questions that Tejinder is asking.
You're saying that perhaps the only spinners he's got are right-handed ones we can ignore.
Well, right-handed ones we have to, I don't know. I want to think about it I want to think about the questions Tejinder is asking before we give my talk. But I think we have to be careful. We don't always go down to just the 2x2 stuff.
Fair enough.
Good.
Right. We have some versions with
brought up Good you brought up chirality, because when I have E8 cross E8, I have E6 cross E6. One E6 for the left-handed 3 generations, the others E6 for the right-handed 3 generations. And the eigenvalues are calculated separately for both the sets. Yeah, great, thank you. Yeah, so maybe getting to closing time. Any more questions, please?
Could I ask just one quick clarificatory question to Corinne and indeed to Tevian? I'm sorry, I may have misunderstood the point, but why are you saying that you can basically ignore or throw away the right-handed spinners in this context?
So that was my comment that comes back to the fact that in various places in the magic square,
Hmm.
the left and right-handed spinners show up either in the 3x3 symmetry group, symmetry algebra that you're looking at in the magic square, or in the representations. And they do so unevenly or not symmetrically.
No,
And so
yes, yes,
if you
yes.
look back in the magic square, you can find a place where some of the spinners have joined the adjoint piece and are no longer being thought of as representations. And that may allow us to bridge the gap between our point of view and Tejinder's.
I understand. I understand the point. Now I understand, as it were, where the right-handed spinners, your remark about right-handed spinners fits into that. Thanks again for the clarification.
Mhm.
Okay, Michael, should we wind up?
I think unless there's anybody who has any further questions or anybody wants to stay online a little bit longer, it's been a fantastically rich and exciting talk today. Thank you once again, Tevian.
so,
Thank you, Corinne. Thank you again
so,
for everybody who took part.
should
We'll see you
mention
back
that
here again on the, is it on the 18th we're
it's
meeting?
the 18th, so we have another exciting talk coming up. Neil Turok very kindly agreed to speak. So it's not on a Friday, it's a Monday. And
Yes.
he'll talk on the CP symmetric universe work he's been doing with Latham Boyle, which I think in some way is related to the kind of things we are discussing in this meeting. Yes.
Yes, and once again, can I underline that unusually that will be on a Monday, the 18th of September, rather than on a Friday, as our talks usually are. Okay, thanks. And Tejinder, I'll contact Igor and his colleague to ask if they could accept an invitation to speak on the 24th of November.
That'll be wonderful. That'll be
Okay.
wonderful.
Right. Well, once again, thank you very much to everybody who's taken part today, but obviously above all to Tevian.
Also, get well soon wishes for Corinne. No,
Yes.
I hate to see COVID still around. The thing doesn't go away. I mean,
No, get well soon.
Thank you all.
yeah, thank you. Okay, I'll log out. Bye bye.
Okay, bye.